Addition reactions to alkenes. Alkenes undergo three types of characteristic addition reactions due to the high reactivity in its double bonds. One type is the hydrogenation reaction, where a hydrogen molecule is added to the carbon-carbon double bond. And the second type is the hydration reaction, where a water molecule as a hydrogen atom on a hydroxyl or OH group is added to the carbon-carbon double bond. And also, at very high temperatures and pressures, alkenes can undergo polymerization reactions as well. I will talk about all of these three types of reactions one by one. Number one, hydrogenation reactions. So, in a hydrogenation reaction, um, hydrogen atoms are added to the carbon atoms of the double bond in the alkane. So, as you see in this figure, um, the hydrogen atoms, the two hydrogen atoms in the H2 molecule can go and attach to the carbon atom, two carbon atoms of the carbon-carbon double bond. Now, as a result, this alkene will convert into an alkane containing carbon-carbon single bond. So this is a very simple reaction, and these reactions are catalyzed by three types of different catalysts: platinum, nickel, or palladium. So the reason we are using catalysts are to speed up the reaction. So that is the hydrogenation reaction mechanism. Now, we can see an example here. If we have this 2-butene alkene, where the carbon-carbon double bond exists in the second position in the carbon chain, what is the product that you get from the hydrogenation reaction? Again, this is a very simple reaction. You just have to add two hydrogen atoms to the carbon-carbon double bond, and as a result, it will convert into CH2 and CH2 instead of CH and CH in the alkene. And once the two hydrogen atoms are added to the carbon-carbon double bond, it becomes an alkane. Butane is the corresponding alkane. So the platinum catalyst is added here to speed up the reaction. Now let's take another example. What is the product of the hydrogenation reaction of the cyclohexene? Now it's very simple. You just have to add two hydrogen atoms. As a result, as you see here, cyclohexene converts into cyclohexane with no double bonds. No double bonds, it only contains CH2s, CH2s once two hydrogen atoms are added. And you can see here the nickel is the catalyst. So the catalyst can be either platinum, nickel, or palladium. Okay, so there are some applications of this hydrogenation reaction. For some purposes of doing hydrogenation reactions are to produce saturated fats from unsaturated fats. So, for example, vegetable oils are unsaturated fats, and if somebody need to convert these unsaturated fats into saturated fats like margarine, they have to do the hydrogenation reaction. So it's just addition of the hydrogen molecule over the double bonds in the unsaturated fats like vegetable oil. They are liquids at room temperature, just like canola oil, olive oil, Um, so they are liquid at room temperature, and those are um, unsaturated fats. So here you can see an example, oleic acid, which is found in olive oil. This oleic acid is a fatty acid containing a double bond. Now, that's why we are saying them as unsaturated, because they don't have the maximum number of hydrogen atoms in this carbon-carbon um, bond. So, um, in the hydrogenation reaction, a hydrogen molecule is added over the carbon-carbon double bond, and it will be converted to stearic acid, which is now a saturated fat. So these saturated fats are solids at room temperature, just like margarine. They have high melting point. So this is the difference between saturated versus unsaturated fats. So in the production of margarine, these hydrogenation reactions are applied. Now let's look at the health effects of this conversion. So if you consume margarine in daily basis, so what can happen? These fats, these solid fats can deposit in blood vessels, and as a result, it can lead to some atherosclerosis condition, which can cause some heart problems, right? Now, on the other hand, uh, the vegetable oil or olive oil, they stay as liquid at room temperatures and their melting points are low, and they are very less likely to form those fat deposits in your blood vessels. So for these reasons, um, saturated fats are known to be less healthy than the unsaturated fats. Okay, now I have this question. So please try to answer this by yourself and then come back and check your answer. Write an equation for the hydrogenation of 1-butane using a platinum catalyst. So I'm going to draw the structure for 1-butane. So it's an alkene containing carbon-carbon double bond in the first position. If I draw the content structural formula, it will looks like this. I need to make sure that all carbon atoms have 4 bonds in the structure. Yeah. Now, what is the product from the hydrogenation reaction? So this is the reaction. So it's asking for an equation. Okay. Now, so after addition of the 2 hydrogen atoms, you will get show. So I can write this hydrogen as in the expanded as an expanded formula to show how the atoms are goes and attached. As a result, it will contain CH3, CH2, CH2, and CH3. And this is 1-butene converts to, what is the name of this one? It's the alkane butane. Okay, very good. So that's the structure or the product for the hydrogenation reaction. And I have another question. Write the product of each of the following. Um, okay, so it's a hydrogenation reaction. So you just have to add two hydrogen atoms into the carbon-carbon double bond. Now there's only one hydrogen here, so it will be two hydrogens once you add the hydrogen molecule. Same here. And you will get butane. And what is the product in here? It's a line angle structure for cyclopentene. So the hydrogen atoms will be added to this carbon and this carbon, and as a result, the double bond will disappear. So the product will be just like this. Okay, so what happens here? There's only one hydrogen atom attached to these two carbons, right? Then once you add the added the hydrogen, it becomes CH2 and CH2. So you don't need to show that. You can just draw it like this. Same molecule. Okay, so those are the products for the hydrogenation reactions. Hydration reactions. So these are the reactions of the addition of a water molecule to the carbon-carbon double bond in the alkenes. Now, when we say a water molecule, we can split this water molecule to show hydrogen and hydroxide group. Now, the hydrogen atom and the hydroxide group will go and attach to the two carbon atoms containing the double bond. And as a result, it will form an alcohol with a functional group of hydroxide group. These reactions are catalyzed by a strong acid such as sulfuric acid, and we show it as an H plus ion, and it is written on the arrow of the equation. Now let's see what exactly happens here. Now, when there's an alkene reacting with concentrated sulfuric acid, the water molecule can breaks up to give hydrogen and hydroxide group, and one hydrogen atom. Okay, the hydrogen atom can go and bind with one carbon atom, and the hydroxide group can go and bind with the other carbon atom. So this is the addition of a water molecule. So the H and OH came from the water molecule. Now, this will lead to a molecule called alcohol, because there is no carbon-carbon double bond here. Instead, you can see a carbon-carbon single bond, and you can see the functional group of alcohol, which is hydroxide in one carbon atom. So the addition of a water molecule or these hydration reactions will convert alkenes into alcohols. So this is the reaction mechanism for addition of water molecule or hydration reaction. Now let's see a simple example. Addition of water to ethane, the simplest alkene. Now this is a very symmetrical alkene, which means both carbon atoms contains the same type of atoms on both sides. And the hydrogen and hydroxide group can go and connect to either of the two carbon atoms. And there's one product possible, which is ethanol, where hydroxide group can go and attach to one carbon group, and the other carbon atom will contain CH3 group. So the product is CH3CH2OH. And the IUPAC name of this compound is ethanol. The generic name is the ethyl alcohol. So this is how you can deduce the product formed from the hydration reaction. Okay, now what happens if the alkene is asymmetric, which means the carbon atoms in the carbon-carbon double bond bonded to different types of groups. And how do you know to where the hydrogen atom goes and where the hydroxide groups go? Because they have their own preferences. Now, in an asymmetric alkene, this is the rule. The hydrogen atom from the water forms a bond with the carbon atom in the double bond with more hydrogen atoms. So this is very important. Okay. The hydrogen atom goes and binds with the carbon that contains more hydrogen atoms. And the hydroxide group will go and bind with the carbon atom with fewer hydrogen atoms. So this is how you know where the hydrogen and hydroxide goes and binds. So that is the rule number 2. So what does this mean? Let's take an example. Now we have this example 2-methyl-2-pentene. The line angle structure is given here. So this is a 5 carbon atoms containing long chain pentene. And the okay, so this is an alkene with 5 carbon atoms and a methyl group attached to the second carbon. Okay, so 1, 2, 3, 4, 5. And we call this as 2-methyl-2-pentene. If you look at this structure, if you take a closer look to the structure, which carbon atom on this alkene, if I say carbon 2 or carbon 3, which one contains a higher number of hydrogen atoms and a lower number of hydrogen atoms? So if you take carbon 2, do you see any hydrogen atoms there? No, because this is a methyl group and this is also a methyl group. This carbon is connected to 2 methyl groups and the other 2 bonds are with the carbon-carbon double bonds. So no hydrogen atoms. Originally there is no hydrogen atoms present in this carbon 2. If you take a closer look at the carbon 3, there is one hydrogen atom here. How do you know? Because this already has 1, 2, 3 bonds. So according to the rule, each carbon has to have 4 bonds. So the invisible bond is with the hydrogen atom. Okay, so this contains 1 hydrogen atom. Okay, now the rule for the hydration reaction is if you take the H and OH. Now this hydrogen will go and bind with the carbon containing higher number of hydrogen atoms. In this case, that will be this carbon. So it will go and attach there. The hydroxyl group will go and bind with the carbon containing the fewer number of hydrogen atoms in the double bond, which is carbon 2. So that will go and bind to this carbon. So that's how you deduce to which carbon where this hydrogen and hydroxide goes and bind. Now let's see the product. So I am going to exit this drawing. Probably it will erase everything. But if that happens, you can go back and check the video. So the product will looks like here as in the figure in your right hand side. Okay. Now the hydroxyl group, you can see it's in the carbon, the second carbon, and the hydrogen is already attached to the third carbon, and the carbon-carbon double bond is disappeared as in any other addition reaction. So this is the new product, and this is also is an alcohol because it contains this hydroxide group. So we call this as an alcohol. This is very important. Every time hydration reactions form alcohols. Alcohols are the ones that contains this hydroxide group. We have another topic on the alcohol, so we will talk in detail in that topic. So for now, just remember the hydration reactions will convert alkenes into alcohols. Okay, now please pause this video and try to answer this question and come back and check your answer. Okay, predict the product of the addition of H-OH, or in other words, H2O, to the following alkene. Now, we do have this 1-butene. This is 1-butene. So what will be the product when you add hydrogen and OH? The first question is, where does this hydrogen goes and where the hydroxide goes? We need to figure that out. According to the rule number 1, the hydrogen will goes and attach to the carbon containing the highest number of hydrogen atoms. Out of these two carbon atoms, the highest number of hydrogen atoms are in this carbon, so it will go and attach to that carbon. The rule number 2 is hydroxide group will go and attach to the carbon with the fewer number of hydrogen atom, which is this carbon. So that will go and attach to this carbon. Okay, now you can draw the product. The product obviously have to be an alcohol. It will be CH3, CH2, CH, OH, and CH3. Okay, so that is an alcohol, which is we call it as 2-butanol. I'm not gonna stress out on the IUPAC names of the alcohol at this point because we have another topic. The structure will be looks like this. Okay. Next topic is polymerization reactions. That is the third type of reactions, addition reactions of alkenes. What is a polymer? So these are very large molecules formed by alkenes, and these the polymers are formed by reacting a repeating unit called monomer. So these monomers are the alkenes. So in plastic industry, there are so many synthetic polymers that are being produced in these days, such as the material that used in plastic wrap, non-stick pans, and plastic cups. So in different type of material, they use different types of polymers. Let's see some examples in our future slides. So these polymerization reactions, it requires very harsh conditions like high temperatures, a catalyst, and high pressures because it needs energy to break up the carbon-carbon double bond in alkenes and to connect the monomers to produce this long chain polymers. So it is an addition reaction because the carbon-carbon double bond disappears and the polymer grows as a long chain containing these monomer units. Let's take one example, polyethylene polymer. So this is the polymer that forms by adding ethylene or ethene, which is given in here. So this is the monomer unit. So by adding up multiple units of ethene, it will end up in a polymer called as polyethylene. Now what exactly happened in here? Now as you see here, you can find the monomer unit as given in this figure in your right hand side. So this is a monomer unit. So can you relate the monomer with this repeating unit? So what exactly happened there? This double bond here, carbon-carbon double bond has disappeared here and it formed a single bond, right? In addition, these two carbon atoms have bonded to two other carbon atoms side by side to make four bonds for each carbon atom. Okay, so you should be able. Let's look at one example of a polymerization reaction. The reaction of ethene monomers to form a long chain polymer, polyethylene. It's a widely used polymer material. Now let's see what exactly happens in this reaction. Now there are three ethene monomers that you see here. As they are added together, what happens to these carbon-carbon double bonds? Now, in the polymer, the corresponding polymer, you don't see these double bonds anymore in between carbon-carbon atoms, right? Because these carbon-carbon double bonds are disappeared in the polymer, corresponding polymer. At the same time, you can see each carbon atom in the double bonds have bonded to two other atoms, two other carbon atoms side by side to make the total of four bonds. Now this is what happens in a polymerization reaction. So the monomer units are added to the end of the chain as the continuation of the polymerization reaction. As a result, the carbon-carbon double bond in the long chain, polymer chain, is disappeared and aids to form a bond with the neighboring monomer's carbon atom. So you should be able to deduce what is the polymer given a monomer unit. So that's the knowledge that we need to abstract from this type of reactions. Okay. Now we'll see some other examples as well. So this table shows some other examples of polymers and their monomer units. We already discussed about ethene and polyethylene. And the second example I want to show is the polyvinyl chloride or PVC. What is the monomer unit of polyvinyl chloride? Obviously, it has to be an alkene. And how to deduce what is the alkene? So just break up a repeating unit. Find out what is the repeating unit in this given polymer. That's the first step to determine what is the monomer unit. Okay, given a polymer, you should be able to identify what is the monomer, and given the monomer, you should be able to draw the possible polymer. Now I'm going to start from the polymer. So if you have a closer look at this long chain polymer, try to understand what is the repeating unit. Now it starts here And I can identify this is one repeating unit, right? And this is another repeating unit. So this is the repeating unit. Now, to convert this into a monomer, just simply add a double bond in between these two carbon atoms. Okay, and as you add a double bond, you will get this structure, which is fluoroethane. Okay, so as you add the double bond at the same time, these two bonds are disappeared. Okay, just add a double bond in between these two carbon atoms. Okay, and that's how you find the monomer unit from the given polymer structure. Now let's look at this example. Um, Synthesis of polypropylene or PP polymer starting from propene. Now I'll go from the monomer to polymer this time. Okay, I'm gonna draw it here. So you have this monomer. Okay, now you need to convert this into a polymer with the repeating unit. So what will be the repeating unit form here? So this is what I'm gonna do. I will just um, add an additional bond to this carbon, and we'll keep the same two hydrogen atoms here, and this the double bond becomes a single bond now and connects the second carbon atom, and the methyl group remains the same. They will remains the same. Any attached groups or atoms to these double bonds will remain the same. The difference, what will be changed, is the bonds. The double bond becomes a single bond. In addition, there will be two additional carbon bonds which will be bonded to the next repeating unit's carbon. So this is the repeating unit. Okay, and we put these square brackets and put in here to show the polymer, to show this is a part of the polymer, the repeating unit of the polymer. It means there can be huge number of n repeating in this polymer. Now, this is the same thing that is drawing here. As you see, this repeating unit is repeated by adding two other monomers together. Okay, I hope you can understand that. So we'll see another example. I think I should have another slide. Yes. So we'll do another example. Now we have this tetrafluoroethane, which is the monomer that is used to make PTFE, or in Teflon. If you are using non-stick pans, so Teflon is the coating that is used in this non-stick pans. It's a polymer called PTFE. So we have this monomer unit called tetrafluoroethane. So let me draw the ethane. Okay, can you convert this into the polymer? Yeah, just follow the same rule that I just mentioned. So I will first draw, let me draw this, taking some space. I'm going to draw it here. So see, the carbon-carbon double bond becomes a carbon-carbon single bond, and the two fluorine atoms in both carbons will remain the same, and there will be an additional bond, and that carbon that bond will be bonded with the second monomer unit's carbon. The second monomer unit is the same repeating unit. Okay. And I'm going to add another monomer, so with 3 repeating units. So this likewise, it will add so many repeating units again and again. So this is a long chain polymer. Okay. So you should be able to convert this monomer into polymer as well as identify what is the repeating unit from the polymer to the monomer as well. So this is another example that you can try just by looking at the polydichloroethylene. It's a polymer that is used in plastic films. So identify the repeating unit. Can you make this repeating unit can you convert this repeating unit into the corresponding monomer, which is the alkene? Yes, you should be able to. Just add a carbon-carbon double bond, carbon-carbon double bond, and then you will get the same molecule, right? Okay, good. And we have this aromatic compounds containing polymer. Phenylethane is the monomer. Um, it is called as styrene, and it is used to make polystyrene. Same principle. So you just take off the double bond in between carbon-carbon atoms and just keep adding the repeating units, bonding with the neighboring monomers. You get polystyrene. Polystyrene is used in plastic coffee cups. Okay, so that's all you need to know under these polymers. Understand how these addition reactions occur and identify the monomers from the polymers and polymers from the monomers.